I would like to now talk about inverse trig functions and specifically the restrictions on inverse trig functions. Consider for a minute the original function sine of theta equals to y over r. In this particular notation, we call theta the input and we call y over r the output. From algebra, we learned that to take an inverse, we basically switch the input and the output. Inverses are also denoted usually with a -1 somewhere in the notation. Here's the notation for sine inverse. We say sine, to denote the inverse, we put a -1, and then instead of plugging in an angle measure, you actually plug in the value of sine, which is y over r, and what you get out is theta. One of the most important things that you need to know about inverses is the thing that you put into the inverse is an actual value, and then the thing that you get out of an inverse is an angle. Let's look at, for a minute, restrictions on inverse functions. By me saying that something is a function, that indicates that for each input there is one and only one output. We know that the graph of sine is actually cyclic. So for example, if we just think about the graph of sine looks something like this. If we took the inverse of that particular function, the inverse of sine as it is not a function by the horizontal line test. We learned in algebra that if you draw a horizontal line through a graph and it crosses more than once, then the inverse is actually not a function. We know that sine also goes back this direction, so the horizontal line test fails on multiple levels there. So what we need to do to make sure that when I take the inverse of a trig function, that my inverse is a function, is we restrict the domain of the original trig function. Let's look at this. Here are my restrictions. I'm going to label this restrictions on original functions so that inverses are also functions. And I'll just do these kind of one at a time. Number one, think about restriction for sine function. To do this, I'm going to consider the graph. What we want to make sure of is we want to make sure that we catch every single possible value for sine. From earlier, we know that the sine values go from -1 to +1. So we want to make sure that we've got every single value from -1 to +1, but that we don't repeat any values. Consider for a minute this part of the sine graph. Let's start at 0 and go ahead to pi over 2, and then let's also go back to -pi over 2. Okay. On the right-hand side, the sine function looks something like this. It goes up to 1, and then above that quarter point of pi over 2, the value is 1. On the left-hand side, we actually go down to -1. And let me move this pi over 2 over so I can see better. On this side, the graph is going to look something like this, and it dips down to -1. If we look at the graph of sine only for the values between -pi over 2 and pi over 2, we can see that sine makes a complete cycle of all its values between negative 1 and 1, but it does not repeat any of those values. So, for the sine to make its inverse a function, what we will do is we will restrict our angles between negative pi over 2 to pi over 2. Now, what this means is it means when we perform an inverse on sine and we're looking for angle measures, that means that we look for angle measures only between negative pi over 2 and pi over 2. Consider this for a moment. If we're looking at axes and we have 0, pi over 2, pi, 3 pi over 2, and 2 pi, me saying that I'm looking for thetas in between pi over 2 and negative pi over 2, we realize that this angle down here, 3 pi over 2, is actually the same as negative pi over 2. So me making this restriction means that I'm looking for angles either in quadrant 1, going the positive direction, or in quadrant 4, but rotating in the negative direction. Let's look at the next restriction. Number 2, for cosine. We'll do something similar as far as looking at the graph. Okay. For cosine, I'm actually going to look at the graph between 0 and pi. Okay, looking at the graph of cosine between 0 and pi, I would start at positive 1. I would go through all of my values in between 0 and pi. And so that's the way the graph looks in between 0 and pi for cosine. You see that every single value between 1 and negative 1 is gotten, but those values are not repeated. So on this particular one, for cosine, the restriction on the angle is anything in between 0 and pi. Okay, considering this, we know 0 is here, pi is there, and so if I'm performing an inverse on cosine, the only place I look is I look at these positive angles either in quadrant 1 or quadrant 2. I'm going to go ahead and make a note because for sine and for cosine, I also know the restriction on the inverses for secant and cosecant, so I'll go ahead and out to the side I'll make that note. Okay, for sine, the reciprocal of sine is cosecant, so I'm going to put in a little note over here on the side. I'm going to say for cosecant of theta, if I'm performing an inverse on it, the restriction is similar, but the only difference is anywhere that sine has got a 0, there's an understood asymptote. And so you have a similar restriction. The only difference is there is one number in the interval that I cannot have, and that number in this case would be 0. So for cosecant, the restriction on theta, and I'm going to write this in a little bit different way, is theta can be anything from negative pi over 2 to 0, don't include the 0, and then union 0 to pi over 2. And so if you know the restriction for sine, you also in a way know the restriction for cosecant. It's the same restriction, only you leave 0 out. Okay, the same thing for cosine. The reciprocal of cosine is secant, so I'm going to make a note over here on the side, and I'm going to say for secant theta, the restriction on theta is this. Secant is not defined where cosine is 0, so you'd have an asymptote in here. That particular quarter point is pi over 2. So the restriction here, you would go from 0 to pi over 2. You don't include that, so I use a parentheses, and then you go from pi over 2 to pi. That's the restriction that you put on theta for secant inverse. There are two others. Number 3, for tangent of theta, this restriction is very straightforward. Okay, we know that for tangent there are asymptotes at the first and last quarter points, negative pi over 2 to pi over 2. The actual graph of tangent looks something like this. And you see that for one period of tangent, we do not go through multiple values of y. So if we use the actual one period location that's normal for tangent, we don't have any trouble with the inverse. So the restriction here on theta is theta can be anything between negative pi over 2 to pi over 2. I just can't include either negative pi over 2 or pi over 2 because there's asymptotes there. Okay, this, if we think about it as far as angles are concerned, that means that when we apply an inverse to tangent, we need to either look up positive angle in the first quadrant, or we need to look a negative angle in the fourth quadrant. Finally, for cotangent, if we consider the graph of cotangent by itself, it has asymptotes at 0 and at pi. The graph will end up looking something like this. And we see that within that normal period that we usually graph for cotangent, there are no repeated y values. We hit every single value, but we don't have any repeated. And so for cotangent, the restriction is similar. It's everything from 0 to pi, not including 0 or pi. That means if we're applying an inverse to cotangent, we look in between 0 and pi. So the first and second quadrants. This concludes the lesson on restrictions on inverse trig functions.